Despite our remarkable progress in understanding the universe, countless mysteries still challenge our most trusted theories. From unexplained forces to strange signals, the universe is teeming with unsolved enigmas. Let's take a close look at phenomena like the Hubble tension and mysterious emissions from our galaxy, and explore ideas that might hold the key to the next big breakthrough in our knowledge about the universe. Beyond the visible, the missing baryon problem in the cosmic web. Everything we see, galaxies, stars, planets, and even ourselves, is made of baryonic matter, the ordinary substance composed of protons and neutrons. Scientists have spent decades measuring and mapping this matter across the cosmos, using telescopes that detect light in every possible wavelength, from visible and infrared to X-ray and radio waves. Yet, despite all their efforts, something doesn't add up. A significant portion of the baryonic matter predicted by theoretical models is missing. Unlike dark matter, which remains undetectable except through its gravitational effects, these missing baryons are supposed to be ordinary matter, the kind that should interact with light and be measurable in some form. And yet, they remain elusive. The problem became clear when scientists compared observations of the universe with theoretical predictions derived from the cosmic microwave background radiation, or CMB, the faint afterglow of the Big Bang. This radiation, mapped in exquisite detail by missions like the Planck satellite, contains information about the composition of the early universe, including how much normal matter should exist. These measurements indicate that baryonic matter should make up about 5% of the total mass-energy content of the cosmos. However, when astronomers tally up all the visible matter in the universe, stars, nebulae, interstellar gas, and galaxies, they can only account for roughly half of what should be there. The rest is missing. This discrepancy puzzled scientists for years. If baryons are normal matter, they should be detectable. Their interactions with light, gravity, and other forces should reveal their presence. But the missing matter was nowhere to be found, raising questions about where it could be hiding. The leading hypothesis suggests that the missing baryons are not in galaxies or interstellar space, but instead lie in the vast, nearly invisible structures that shape the large-scale cosmos, the cosmic web. The cosmic web is an immense interconnected network of filaments made of gas and dark matter that weaves through the universe. Galaxies and galaxy clusters are not randomly scattered. Instead, they are arranged along these filaments, forming a structure that spans billions of light years. The spaces between galaxies are not empty, but contain thin, diffuse clouds of gas. Scientists now believe that this intergalactic medium is the key to solving the missing baryon problem. The missing matter may be spread throughout these filaments, in a form that makes it incredibly difficult to detect. Astronomers refer to this hidden matter as the warm-hot intergalactic medium, or WIM. It is thought to be made of extremely thin, hot gas, with temperatures ranging from 100,000 to 10 million degrees Kelvin. At such high temperatures, the gas does not emit visible light like a star. Instead, it glows faintly in ultraviolet and X-ray wavelengths, making it incredibly hard to observe with traditional telescopes. While this gas is thought to be abundant, its density is so low, only a few atoms per cubic meter, that it remains almost invisible even to the most advanced instruments. Detecting the WIM has required innovative techniques. One of the most successful approaches involves looking for absorption lines in the light from distant quasars. Quasars are among the brightest objects in the universe, shining from billions of light years away. As their light travels across the cosmos, it passes through intergalactic gas, where specific elements like oxygen, carbon, and hydrogen absorb certain wavelengths of light. By analyzing the missing parts of the spectrum, astronomers can infer the presence of hot, ionized gas in the cosmic web. X-ray telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have provided some of the first direct evidence of this missing matter. By studying the light from quasars that pass through filaments of the cosmic web, researchers have detected highly ionized oxygen, a strong indicator that hot, diffuse gas exists in intergalactic space. However, these signals are incredibly weak, making the search a slow and painstaking process. Another breakthrough came from an entirely different approach: fast radio bursts, or FRBs. These mysterious, ultra-powerful pulses of radio waves originate from distant galaxies and last only milliseconds. As these bursts travel through intergalactic space, they interact with free electrons, causing slight delays in different wavelengths of the signal. By measuring these delays, scientists can estimate the total amount of matter the signal passed through. Recent studies using FRBs have provided strong evidence that the missing baryons are indeed lurking in the cosmic web, spread out as a thin, hot gas between galaxies. Because this gas is spread out over vast distances, its X-ray emissions are incredibly weak. Most current telescopes struggle to detect them with confidence, leading to uncertainties in the exact amount of missing matter they contain. To overcome this, astronomers have turned to a different kind of observational trick, using galaxy clusters as cosmic magnifying glasses. This method, known as gravitational lensing, takes advantage of how massive objects bend and distort light from background sources. When a distant quasar or galaxy lies behind a massive cluster, the gravity of the cluster bends and amplifies the light, allowing astronomers to study details that would otherwise be too faint to detect. By using this technique in combination with X-ray observations, researchers have been able to strengthen the evidence for baryons hidden in the intergalactic medium. While observations suggest that much of the missing baryonic matter is in the WIM, astronomers are still working to map its exact distribution and confirm its total mass. The WIM is not uniform. It is clumpy, structured, and constantly evolving. Some parts of the cosmic web may contain more baryons than others, and different detection methods may be sensitive to different parts of the structure. X-ray telescopes are best at finding the hottest and densest regions, while fast radio bursts can probe more diffuse areas. This means that no single technique can fully reveal the missing baryons on its own. Instead, astronomers must combine multiple methods, cross-checking their results to build a more complete picture of the intergalactic medium. Some scientists believe that additional baryons may exist in even harder-to-detect states, such as ultra-hot plasma or energetic outflows from galaxies. The upcoming Athena X-ray Observatory, scheduled for launch in the 2030s, is designed specifically to study the hot gas in the cosmic web. With significantly greater sensitivity than current instruments, Athena will provide a much clearer picture of how baryons are distributed in intergalactic space. Other missions, such as the Square Kilometre Array, a massive radio telescope network currently under development, will refine our ability to use fast radio bursts as cosmic probes, helping to further map the missing matter. The distribution of baryonic matter affects how galaxies form, how they interact, and how the universe itself has evolved over billions of years. If a large fraction of normal matter exists in the cosmic web, it means that the spaces between galaxies play a far greater role in cosmic evolution than previously thought. The missing baryons could be part of a continuous cycle, flowing in and out of galaxies, fueling star formation, and shaping the universe in ways we barely understand. Cosmic ray conundrums, tracing the origins of ultra-high energy particles. Traveling at nearly the speed of light, cosmic rays constantly bombard Earth from all directions. While many cosmic rays are relatively low-energy particles originating from the Sun or supernova remnants, some possess an energy so extreme that they defy our current understanding of astrophysical processes. These ultra-high energy cosmic rays, or UHECAs, arrive with energies millions of times greater than anything humanity has ever produced in a particle accelerator. Scientists first discovered cosmic rays in the early 20th century, when balloon experiments detected an unexpected level of ionization in the atmosphere. Over time, researchers identified that these particles were primarily protons and atomic nuclei, traveling through space at high velocities. Most cosmic rays are relatively low in energy, but a small fraction arrive with energies so extreme that they must have originated from the most violent astrophysical events. These include exploding stars, active galactic nuclei, and possibly even unknown sources beyond our current understanding. The most energetic cosmic ray ever detected, known as the Oh My God particle, struck Earth in 1991 with an energy of around 320 exa-electron volts, equivalent to a fast-pitched baseball hitting a glove. This single proton carried more energy than any particle ever observed from space, and yet its source remains a complete mystery. The challenge is that such high-energy cosmic rays should interact with the CMB, losing energy as they travel through space. This process, known as the Greisen-Zatsepin-Kuzmin, or the GZK limit, suggests that UECRs should not be able to travel vast cosmic distances without being slowed down. Yet particles like the Oh My God cosmic ray arrive on Earth, seemingly defying this theoretical limit. Unlike light, which follows a straight path through space, cosmic rays are charged particles, meaning they are influenced by magnetic fields along their journey. The interstellar and intergalactic magnetic fields bend and scatter these particles, making it difficult to trace their trajectories back to their sources. When a cosmic ray enters Earth's atmosphere, it collides with molecules in the upper atmosphere, creating a cascade of secondary particles that spread out over vast distances. Scientists use massive ground-based detectors, such as the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, to study these air showers and determine the properties of the original cosmic ray. Most cosmic rays are protons, but some are heavier nuclei like iron or carbon. Ultra-high energy cosmic rays, however, could be something even more exotic. Some studies suggest that they might contain unexpected particles that do not fit within the standard model of physics. If this is true, it could point to new fundamental physics at play in the highest energy environments in the universe. One leading theory is that UAECRs are accelerated by powerful shockwaves surrounding active galactic nuclei, supermassive black holes at the centers of galaxies that produce vast jets of energy. Another possibility is that they come from gamma-ray bursts, some of the most energetic explosions in the universe. These bursts, caused by either the collapse of massive stars or the collision of neutron stars, release enormous amounts of energy in just seconds. If cosmic rays are accelerated in such extreme environments, they could be launched across the universe at nearly the speed of light. Some researchers have speculated that these particles might be produced by the decay of hypothetical supermassive particles left over from the early universe. These particles, often associated with grand unified theories or even string theory, could release high-energy cosmic rays as they break down. Others have suggested that cosmic rays might be linked to topological defects in space-time, such as cosmic strings, hypothetical cracks in the fabric of space left over from the early moments of the cosmos. Despite decades of research, the origins of the most energetic cosmic rays remain unknown. Some of the biggest surprises have come from the apparent lack of clear sources. If UECRs originated from powerful astrophysical sources like active galaxies, scientists would expect to see correlations between the arrival directions of these particles and known galactic nuclei. However, studies have shown that the highest energy cosmic rays appear to come from random directions, with no obvious connection to nearby galaxies or other known sources. Scientists are now using space-based telescopes, such as NASA's upcoming Probe of Extreme Multi-Messenger Astrophysics, or POEMA, which will detect cosmic rays by observing the ultraviolet flashes they produce in Earth's atmosphere. By studying these particles from above, researchers hope to bypass the limitations of ground-based detectors and get a clearer picture of where these mysterious rays are coming from. If ultra-high energy cosmic rays are being produced by unknown processes, they could reveal physics beyond what the Large Hadron Collider or any human-made experiment can achieve. They may even offer clues about quantum gravity, extra dimensions, or dark matter interactions. The Hubble conundrum, discrepancies in cosmic expansion rates. Nearly a century ago, astronomer Edwin Hubble found that distant galaxies were moving away from us, and the farther they were, the faster they seemed to be receding. This observation led to the idea that the universe itself is expanding, stretching space between galaxies over time. The rate of this expansion, known as the Hubble constant, is a crucial number in understanding the history and future of the cosmos. But in recent years, a troubling problem has emerged. Different methods of measuring this expansion do not agree. This discrepancy, known as the Hubble tension, has become one of the biggest unsolved mysteries in astrophysics. Scientists have two main ways of determining the Hubble constant. The first method involves measuring distances to nearby galaxies using objects called standard candles. These are astronomical objects with known brightness, allowing astronomers to calculate how far away they are based on how dim they appear. One of the most reliable standard candles is a type of exploding star known as a Type Ia supernova. These supernovae always explode with roughly the same luminosity, making them useful for measuring vast cosmic distances. By combining these distance measurements with the speed at which galaxies are moving away, scientists can calculate the local expansion rate of the universe. The second method relies on an entirely different approach, measuring the universe's expansion from its earliest moments. This is done by studying the CMB. This afterglow, first discovered in 1964, provides a snapshot of the universe when it was just 380,000 years old. Scientists analyze tiny temperature variations in the CMB to determine the universe's initial conditions, including how fast it was expanding at that time. They then use mathematical models based on the laws of physics to predict how fast the universe should be expanding today. The problem is that these two methods do not produce the same result. Measurements based on the CMB, taken by satellites like Planck, suggest a Hubble constant of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec, a distance of about 3.26 million light-years, the universe expands by 67.4 kilometers per second. However, direct measurements from standard candles and supernovae, using telescopes like Hubble and more recently the James Webb Space Telescope, give a higher value of around 73 kilometers per second per megaparsec. The difference may seem small, but it is significant enough that it cannot be explained by simple errors in measurement. It suggests that something fundamental about our understanding of the universe is missing. Scientists have proposed several possible explanations for this discrepancy. One possibility is that there is an unknown error in one of the methods. Perhaps the calibration of standard candles is slightly off, or maybe there is an overlooked factor affecting CMB calculations. But years of testing and reanalyzing data have failed to find a clear mistake that would account for the difference. Another possibility is that new physics is needed to explain the discrepancy. The standard model of cosmology assumes that the universe is made up of dark energy, dark matter, and normal matter, all of which influence how space expands. But what if this model is incomplete? Some researchers suggest that an unknown force or particle could be altering the expansion rate in a way that current theories do not account for. One idea is that dark energy may not be constant over time, as previously thought. If dark energy evolved differently than expected, it could cause the local expansion rate to differ from what is predicted based on the early universe. Other theories propose the existence of new particles, sometimes called dark radiation, that could have affected the early expansion of the universe. These particles would not be part of the standard model of physics, but could have influenced the CMB in ways that changed the predicted Hubble constant. Some even suggest that the discrepancy might hint at modifications to Einstein's general theory of relativity, which has been the foundation of cosmology for over a century. Recent advancements in observational technology have allowed scientists to refine their measurements further, but instead of resolving the tension, the discrepancy has only become more pronounced. The latest observations from the SH0 or supernova H0 for the equation of state project using Hubble data confirm a higher Hubble constant, while studies of the CMB continue to support the lower value. The way we measure distances across the universe depends on assumptions about the structure of space and how galaxies move within it. If those assumptions need revision, it could change how we interpret the expansion rate. Cosmic timekeepers, rethinking chronometers amidst expansion discrepancies. To fully grasp the history of the universe's expansion, scientists must accurately measure cosmic time. The Hubble tension suggests that something in our understanding may be incomplete. Traditional methods have provided essential clues, but their disagreement signals a need for new techniques. By turning to alternative cosmic chronometers, researchers aim to refine our measurement of time on a cosmic scale and uncover whether this tension is a sign of unknown physics or simple measurement errors. One promising method involves using massive old galaxies as natural cosmic clocks. These galaxies formed their stars billions of years ago, and by studying their chemical composition, astronomers can estimate how much time has passed since their formation. Unlike stars in younger galaxies, which continue to evolve and form new generations, these ancient galaxies have remained largely unchanged. Their stellar populations serve as a record of cosmic history, offering a direct way to measure time across vast stretches of space. By tracking similar galaxies at different distances, scientists can observe how the universe's expansion has evolved over billions of years. Another technique focuses on quasars, the incredibly bright centers of galaxies powered by supermassive black holes. Unlike supernovae, which explode and fade away, quasars shine steadily for long periods, but vary in brightness in a way that can be studied. Researchers have found that the fluctuations in quasar light follow patterns that may be linked to their intrinsic brightness. If these patterns can be reliably understood, quasars could serve as another standard candle, allowing astronomers to measure cosmic distances and refine calculations of the universe's expansion rate. Since quasars are visible at much greater distances than supernovae, they could help fill in the gaps between current observations. When two neutron stars or black holes merge, they create a burst of gravitational waves, ripples in space-time, that travel across the universe. These waves carry a predictable energy signature, which means scientists can determine how far away the event occurred without relying on assumptions about its brightness. These mergers serve as standard sirens, providing an independent way to measure the expansion of the universe. The first detection of a neutron star merger by the LIGO and Virgo collaborations in 2017 demonstrated the potential of this method. As more such events are observed, astronomers will be able to build a timeline of cosmic expansion that is independent of traditional methods. Galaxies are not distributed randomly, but follow patterns shaped by the influence of gravity and cosmic expansion. One of the key features in this structure is called baryon acoustic oscillations, or BAOs. These are remnants of sound waves that traveled through the hot plasma of the early universe before it cooled. The imprint of these waves left a distinct scale in the way galaxies are arranged, creating a cosmic ruler that can be used to measure distances over time. By analyzing how this ruler has changed over billions of years, scientists can gain insights into the rate at which the universe has expanded. BAOs serve as a crucial cross-check against other methods. Another cutting-edge approach is 21-centimeter cosmology, which focuses on the faint radio signals emitted by neutral hydrogen. This signal, which comes from the most abundant element in the universe, is incredibly weak but holds a wealth of information. Unlike visible light, which can be blocked by dust and other obstacles, radio waves travel freely across vast distances. By mapping these signals from different epochs in cosmic history, astronomers can trace how the structure of the universe has evolved. This method is particularly useful for studying the dark ages of the cosmos, the period before the first galaxies and stars formed. Understanding how the universe expanded during this early time could shed light on the source of the Hubble tension. Supernovae remain one of the most well-tested cosmic chronometers, but researchers are looking at new ways to improve their accuracy. Type Ia supernovae have long been used, but recent studies suggest that there may be slight variations in their brightness depending on their environment. If these differences are not accounted for, they could introduce small errors into cosmic distance measurements. Scientists are refining their models of supernova physics and looking for ways to correct for these variations. New surveys using advanced telescopes are expected to improve the reliability of supernova-based measurements and provide an even clearer picture of cosmic expansion. Even black holes may hold clues about cosmic time. The number and distribution of black holes across different epochs could reveal patterns in how the universe has evolved. Black holes form when massive stars collapse, and their growth through mergers could be linked to the expansion history of the cosmos. Future gravitational wave detections will allow scientists to study these mergers in greater detail, potentially offering a new way to trace the passage of time on a cosmic scale. Despite the promise of these methods, challenges remain. Some require highly sensitive instruments that are still being developed, while others depend on detecting incredibly faint signals. Gravitational wave observatories, for example, must filter out noise from countless other cosmic and terrestrial sources to isolate the true signal of distant mergers. Similarly, 21-centimeter cosmology requires careful calibration to separate the hydrogen signal from other radio sources. However, as technology improves, these challenges are gradually being overcome. Whether these new methods confirm our existing models or point to a deeper mystery remains to be seen, but they are opening new doors in the quest to understand the fundamental nature of space and time. Intergalactic shadows, unseen structures in the cosmic web. The large-scale structure of the universe is often described as a cosmic web, an immense network of filaments, clusters, and voids stretching across billions of light-years. These filaments, made mostly of dark matter and gas, form the backbone upon which galaxies and galaxy clusters grow. Yet, not all parts of the cosmic web are equally visible. In between the glowing galaxies and dense clusters, there are vast, nearly invisible regions, low-density shadows that remain difficult to detect. The cosmic web emerged from the tiny fluctuations present in the early universe, regions of slightly higher density that grew over time due to gravity. Over billions of years, matter clumped together, forming long filaments and dense nodes where galaxies and clusters gathered. However, between these structures exist vast intergalactic spaces, regions where matter is present in much lower concentrations. These areas, known as cosmic voids or low-density intergalactic mediums, are not completely empty. Instead, they contain diffuse gas, dark matter, and possibly even undiscovered forms of exotic matter. Unlike stars, which shine brightly, or galaxies, which radiate energy across the spectrum, the matter in these low-density regions is spread too thin to be easily observed. Scientists have developed clever techniques to map these regions indirectly. One approach is to use the light from quasars. As it travels across the universe, the light passes through these faint regions, leaving behind a subtle imprint in the form of absorption lines in the quasar's spectrum. The Lyman alpha forest, a collection of hydrogen absorption lines seen in quasar light, has provided crucial insights into the distribution of gas in the cosmic web. By analyzing these absorption patterns, astronomers can trace the locations of filaments and the less visible gas between them. Another method involves gravitational lensing, where the presence of dark matter distorts the light of background objects. By measuring these distortions, scientists can infer the presence of invisible structures, including the faintest strands of the cosmic web. These intergalactic shadows play an important role in the evolution of galaxies. As matter flows through the cosmic web, these regions act as reservoirs, slowly feeding galaxies with the gas needed to form new stars. However, the dynamics of this process are not yet fully understood. Some studies suggest that these low-density regions could influence how galaxies evolve by controlling the rate at which they receive new material. There is also growing evidence that the distribution of these hidden structures could affect the expansion of the universe itself. Dark energy may not be uniformly distributed. Some models suggest that the way dark energy interacts with the cosmic web could vary based on the density of these intergalactic regions. If this is true, then the unseen parts of the cosmic web might hold crucial information about the nature of dark energy and how it has shaped the cosmos over time. Some theories propose that dark matter might behave differently in these regions compared to denser parts of the universe. If dark matter has subtle interactions beyond gravity, these effects might be more noticeable in low-density environments where other forces do not dominate. Observing these regions in greater detail remains a major challenge. New computer simulations continue to refine our understanding of the cosmic web, helping to predict where these hidden regions might exist and what role they play in the grand story of the universe. Gravity unbound. Questioning the foundations of general relativity. Gravity is one of the fundamental forces of nature, shaping the motion of planets, stars, and galaxies. For more than a century, Einstein's general theory of relativity has stood as the best explanation for how gravity works, describing space-time as a flexible fabric that bends under the influence of mass. This theory has passed every test within our solar system, from the precise orbit of Mercury to the bending of light around massive objects. But on the largest cosmic scales, where the entire universe comes into play, cracks may be forming in this understanding. Observations of distant galaxies show that space is not only expanding, but doing so at an accelerating rate. This discovery, made in the late 1990s, took physicists by surprise. Under general relativity, gravity should act as a force that slows down the expansion over time, as all matter attracts other matter. Instead, the expansion is speeding up, as if some unknown force is pushing galaxies apart. To make the equations work, scientists introduced the concept of dark energy. But dark energy is not something that has been directly detected. It is a placeholder for an effect that general relativity cannot explain on its own. Another troubling issue arises when looking at galaxies themselves. According to Einstein's equations, the stars and gas in a galaxy should orbit its center at speeds determined by the visible mass within it. But when astronomers measure these speeds, they find that stars in the outer regions of galaxies are moving much faster than expected. If gravity behaves strictly as general relativity predicts, these galaxies should be flying apart. Instead, they hold together as if an unseen mass is providing extra gravitational pull. This has led to the idea of dark matter. Like dark energy, dark matter has not been directly observed, only inferred from its gravitational effects. Some physicists believe that these mysteries point to a deeper problem. Instead of adding invisible components like dark matter and dark energy to make general relativity work, perhaps the theory itself needs modification. This idea is not new. Throughout history, scientific theories have evolved when unexplained phenomena could no longer be ignored. Newton's laws of motion, for example, were incredibly accurate for describing everyday forces, but they failed to explain the extreme speeds and massive gravitational fields of the cosmos. Einstein's theory replaced Newton's by showing that gravity is not a force acting at a distance, but the warping of space-time itself. Now, some researchers are asking whether general relativity might also be incomplete. One alternative theory is known as modified Newtonian dynamics, or MOND. It suggests that at extremely low accelerations, such as those found in the outer edges of galaxies, gravity behaves differently than general relativity predicts. Instead of needing dark matter to explain why galaxies stay together, MOND proposes that gravity itself is stronger in these regions than Einstein's equations suggest. While MOND has successfully explained some galactic rotations without the need for dark matter, it struggles on larger cosmic scales. It does not fully account for the observed distribution of galaxies in the universe or the patterns seen in the cosmic microwave background radiation. Another possibility is that gravity does not operate solely within our four-dimensional spacetime, but is influenced by hidden dimensions. The idea comes from string theory, which suggests that the universe may have extra dimensions beyond the ones we experience. If gravity leaks into these hidden dimensions, it could explain why it appears weaker on cosmic scales, potentially offering an alternative explanation for the accelerated expansion of the universe. However, string theory remains highly theoretical, and no experiment has yet confirmed the existence of extra dimensions. In general relativity, the relationship between mass and curvature is fixed, meaning that objects of the same mass will always bend spacetime in the same way. But in the FR theory of gravity, this relationship can shift depending on the scale being observed. Some versions of this theory suggest that at galactic scales, gravity behaves more strongly than expected, potentially eliminating the need for dark matter. Others propose that at the largest cosmic distances, gravity weakens, which could explain the accelerated expansion of the universe without introducing dark energy. One other approach is entropic gravity, an idea that suggests gravity is not a fundamental force, but instead an emergent effect of underlying quantum processes. In this view, gravity is similar to temperature. It is not a basic interaction like electromagnetism, but rather the result of microscopic movements and arrangements of particles. This theory is built on the concept that space itself has a kind of information structure, and as particles rearrange within this structure, what we experience as gravitational attraction emerges as a statistical effect. While entropic gravity remains a developing idea, it provides a completely different way of thinking about how gravity operates, shifting the focus from a force between masses to an effect of deeper physical laws. Even black holes, once considered strong evidence for general relativity, are raising new questions. Recent observations of merging black holes have revealed unexpected features, such as higher than expected masses and unusual spin alignments. Some scientists suspect that these mergers may be revealing new physics at the limits of gravity's reach. Some researchers have suggested that gravity might be connected to another force entirely rather than existing as a separate interaction. The idea of emergent electromagnetism, for example, explores the possibility that gravity and electromagnetism are two aspects of the same underlying force. If this were true, it could lead to a completely new way of unifying the fundamental forces of nature, changing the way we understand how matter and energy interact on the largest scales. The Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s, will detect low-frequency gravitational waves that travel across billions of light-years, providing a new way to study how gravity behaves over cosmic distances. Other experiments are testing the influence of gravity on quantum particles, searching for signs that the force does not behave as expected at microscopic levels. Quantum gravity frontiers, bridging the macro and microcosmos. At the heart of modern physics lies a deep, unresolved problem. On one side is general relativity, which describes how massive objects warp space and time. On the other is quantum mechanics, which governs the unpredictable behavior of tiny particles like electrons and photons. Both theories work well in their respective domains, but they seem incompatible with each other. Scientists are searching for a theory of quantum gravity that can bridge this gap, offering a single framework to explain both the vast cosmic web and the invisible quantum world beneath it. In general relativity, space and time form a smooth fabric that bends under the influence of mass and energy. But in quantum mechanics, reality at the smallest scales is not smooth. It is uncertain and chaotic, ruled by probability rather than definite outcomes. If space-time itself is subject to quantum fluctuations, it may not be the continuous backdrop that general relativity assumes. Instead, it could be made up of discrete units, much like how matter is composed of atoms. The question is, what are these fundamental building blocks of space-time, and how do they shape the universe on both small and large scales? One possible answer comes from loop quantum gravity, a theory that suggests space is not continuous but woven from tiny loops of energy. These loops form a network, similar to a three-dimensional web where the very fabric of space is composed of quantum units. In this model, gravity is not a smooth force, but an emergent property of these tiny structures. If loop quantum gravity is correct, it could explain what happens inside black holes, where general relativity breaks down. Instead of a singularity, a point of infinite density, there may be a highly compressed quantum structure that prevents space from collapsing entirely. In string theory, gravity emerges naturally as one of the possible interactions between strings. The theory also suggests that gravity may be weaker than other forces because it spreads out into extra dimensions, while forces like electromagnetism remain confined to our familiar four-dimensional space-time. Some versions of string theory even predict the existence of minuscule black holes that could be created in high-energy particle collisions, offering a potential way to test the theory in the lab. Physicists are also exploring the idea that gravity itself may not be a fundamental force at all. One such idea is holographic gravity, which proposes that the entire universe may be like a hologram, where three-dimensional space emerges from a lower-dimensional reality. This concept comes from the study of black holes, which seem to store all the information about the objects that fall into them on their two-dimensional surfaces. If this principle applies to the whole universe, it could mean that the three-dimensional world we experience is just a projection of quantum information stored in a lower-dimensional space. As physicists continue to explore these frontiers, the search for quantum gravity remains one of the most exciting challenges in science. Spectral riddles, the enigma of diffuse interstellar bands, DIBs. When light from distant stars travels across the cosmos, it passes through vast clouds of interstellar gas and dust, which absorb specific wavelengths, leaving behind telltale imprints in the spectrum of the starlight. These absorption lines serve as cosmic fingerprints, allowing scientists to determine the chemical composition of the intervening material. Some of these lines correspond to well-known elements and molecules, hydrogen, carbon, oxygen, revealing their presence in the vast emptiness of space. But scattered throughout the spectrum are strange, unidentified features, the diffuse interstellar bands, or DIBs. Unlike typical absorption lines, which can be traced back to specific atoms or molecules, DIBs do not match the signature of any known substance. First noticed in the early 20th century, more than 500 of these bands have been detected at different wavelengths, from the visible to the near-infrared. Some are sharp and well-defined, while others appear broad and diffuse, blending softly into the surrounding spectrum. They seem to be everywhere, appearing in the light of stars across the galaxy, and even in distant galaxies beyond our own. Their near-universal presence suggests that whatever is causing them must be a fundamental component of the interstellar medium, yet no single molecule has been definitively identified as the source. One of the biggest challenges in solving the DIB mystery is the sheer variety of these features. Their wavelengths shift slightly, depending on the environment, hinting that they may not come from a single type of molecule, but rather from a family of related compounds. Some scientists suspect that DIBs originate from complex organic molecules, possibly large carbon-based structures floating in space. Polycyclic aromatic hydrocarbons, or PAHs, have been considered a strong candidate. These molecules, composed of rings of carbon atoms, are known to be abundant in space and are thought to play a role in the formation of interstellar dust. PAHs are incredibly resilient, capable of withstanding the harsh radiation of space while drifting through the interstellar medium. They are known to absorb ultraviolet and visible light, making them a prime suspect for the DIBs. Observations have shown that PAHs are widespread in the galaxy, particularly in regions where new stars are forming. When these molecules interact with ultraviolet light from young stars, they become ionized and undergo subtle shifts in their absorption patterns. Some of these shifts appear to line up with certain DIBs, suggesting that PAHs or related structures could be responsible for at least some of the observed bands. However, while laboratory experiments have confirmed that PAHs produce absorption features, they have not yet matched the full range of DIB wavelengths. Another possibility is that DIBs come from ionized fullerenes, hollow, cage-like molecules made entirely of carbon. These structures, resembling tiny soccer balls, have been found in meteorites and have even been detected in space, such as in the planetary nebula TC-1. Some specific fullerenes, such as C60+, have absorption features that resemble a few of the DIBs, suggesting they could contribute to the overall puzzle. But again, they do not explain all of the observed bands, and their role in interstellar chemistry remains unclear. Some have proposed that these features could be linked to unknown interstellar minerals, tiny solid particles that absorb light at specific wavelengths. Others suggest that DIBs might arise from quantum effects in complex molecular systems, meaning that their origin could be tied to fundamental physics rather than simple chemistry. Some researchers have even speculated about the presence of entirely new types of molecules that have never been observed on Earth, existing only in the extreme conditions of deep space. Advancements in spectroscopy and telescope technology have helped refine our understanding of DIBs. Some DIBs appear stronger in certain regions of space, while others fade or shift depending on the density and composition of interstellar clouds. These variations suggest that environmental factors, such as radiation from nearby stars or interactions with cosmic rays, could influence the molecules responsible for DIBs, making identification even more complicated. Laboratory experiments aim to recreate interstellar conditions by exposing molecules to extreme ultraviolet radiation, low temperatures, and high vacuum environments, simulating the harsh realities of space. These experiments help determine how potential candidates might absorb light under cosmic conditions. Computational chemistry has also played a role, with scientists using supercomputers to model the behavior of large molecules and predict their spectral signatures. One of the latest tools in the hunt is machine learning. By training artificial intelligence to analyze vast amounts of spectral data, scientists hope to identify subtle patterns that might provide new insights into their origins. AI can sift through millions of spectral lines, comparing observations from different regions of space and identifying correlations that would be difficult for a human to spot. While these approaches have narrowed down the list of possible sources, a definitive identification remains elusive. Anomalous trajectories, the Flyby anomaly and its orbital oddities. The gravity assist maneuver is one of the most useful techniques in spaceflight. It allows spacecraft to gain speed without using extra fuel by flying close to a planet and borrowing some of its momentum. This method has been used in almost every major deep space mission, from the Voyagers to modern probes like Juno and Parker Solar Probe. When a spacecraft approaches a planet, it enters the planet's gravitational field. The spacecraft speeds up as it is pulled toward the planet, then swings around and departs in a different direction. If the spacecraft's motion is aligned correctly, the planet's movement adds to its velocity. In simple terms, the spacecraft steals a small amount of energy from the planet's orbit, though the change in the planet's motion is so tiny that it is unnoticeable. The motion of spacecraft is one of the most precisely calculated aspects of modern space exploration. Engineers use well-established laws of physics to predict exactly how a spacecraft will travel as it swings around planets and moons. Yet, in a handful of cases, something strange has happened. Some spacecraft, during their flybys of Earth, have experienced tiny but unexplained changes in speed. These deviations, known as the Flyby anomaly, are small, just a few millimeters per second, but they remain unexplained. The first clear case was noticed in 1990, when NASA's Galileo spacecraft flew past Earth on its way to Jupiter. As it used Earth's gravity to gain speed, its velocity changed by slightly more than calculations predicted. Scientists had carefully calculated that Galileo's speed after the flyby should be 8,949.89 meters per second. But when they measured it, the spacecraft was moving 3.92 millimeters per second faster than expected. At the time, the discrepancy was too small to attract much attention, and many assumed it was a minor measurement error. But why is explaining such a minor change important anyway? Well, this might seem like an insignificant difference, but in space navigation, even tiny discrepancies matter. A spacecraft traveling at the wrong speed can end up in the wrong orbit, potentially missing its target completely. Engineers and scientists checked for any possible errors in tracking equipment, but the data remained consistent. The speed change was real, but there was no clear reason for it, and when more flybys were analyzed, a pattern began to emerge. In 1998, the Near-Earth Asteroid Rendezvous, or NEAR spacecraft, also experienced an unexplained speed increase, in this case a gain of 13.46 millimeters per second, when it passed by Earth on its way to study the asteroid Eros. The same happened to NASA's Cassini probe in 1999 and the European Space Agency's Rosetta mission in 2005. Each time, careful calculations predicted one speed, but the spacecraft ended up moving slightly faster than expected. Scientists have spent years trying to figure out what is causing this anomaly. The usual explanations, such as errors in tracking equipment or slight miscalculations, have been ruled out in most cases. The effect appears to be real, but there is no clear reason why it happens. One of the most intriguing aspects of the anomaly is that it doesn't seem to be random. The amount of unexpected acceleration appears to be related to the angle of the spacecraft's trajectory as it passes Earth. Some researchers have suggested that the anomaly could be caused by subtle effects related to Earth's gravity. General relativity predicts that massive objects like Earth warp space-time, and some have wondered if there could be additional, unnoticed warping effects near the planet that slightly alter the motion of passing spacecraft. However, no existing version of general relativity predicts an effect of this size, making it difficult to support this idea. Earth is not a perfect sphere. It is slightly flattened at the poles, and its mass is not distributed evenly. These irregularities can affect how gravity interacts with passing objects. Some scientists have suggested that subtle variations in Earth's gravitational field could cause small shifts in a spacecraft's trajectory, leading to unexpected speed changes. However, this idea has not yet been confirmed with detailed models. Another possibility is that the anomaly is caused by an overlooked atmospheric effect. Earth's atmosphere extends much farther into space than most people realize, and even at high altitudes, there are still trace amounts of air particles. If a spacecraft were to pass through a region of slightly denser atmospheric gases, it could experience a small push. However, this idea also has problems. The amount of acceleration seen in these flybys is too large to be explained by the known density of the upper atmosphere. Some have proposed that thermal radiation might be playing a role. Spacecraft generate heat from onboard instruments and from sunlight. If this heat is radiated unevenly, it can create a tiny thrust, an effect known as asymmetric thermal radiation. This has been observed in other spacecraft, such as the Pioneer probes, which gradually drifted off course due to heat radiating from their electrical systems. But in the case of the Flyby anomaly, the pattern of acceleration does not match what would be expected from thermal radiation alone. More controversially, some physicists have speculated that there could be a slight modification to the laws of motion that only becomes noticeable under certain conditions, such as when an object moves at high speed relative to Earth's rotation. This idea is purely hypothetical, but it is not the first time that anomalies in spaceflight have led to major discoveries. The orbit of Mercury, for example, did not match predictions based on Newtonian gravity, and it was only explained when Einstein's theory of general relativity introduced the idea that gravity itself warps space and time. There is also the possibility that the effect is linked to the way radio signals interact with the spacecraft. Ground stations track spacecraft by bouncing radio waves off them and measuring the time it takes for the signal to return. If something in the spacecraft's environment, such as unexpected atmospheric interactions or unmodeled radiation effects, causes a slight distortion in these signals, it could create the illusion of a velocity change where none actually exists. Despite numerous studies, the Flyby anomaly remains unsolved. Some spacecraft, like the Juno probe, which flew past Earth in 2013, did not show any unexplained acceleration, adding to the mystery. If the anomaly were caused by a simple error in calculations, it should affect all spacecraft in the same way. The fact that it only appears in some cases suggests that there is still something about these flybys that scientists do not fully understand. To gather more data, space agencies have considered designing specific flyby experiments that would test different variables, such as trajectory angles and altitudes, to see when and where the anomaly occurs. However, space missions are expensive, and adding tests specifically for this anomaly has not been a priority. Instead, scientists continue to analyze data from past flybys, looking for patterns that might provide new insights. Even in this modern era of space exploration, there are still unexplained phenomena hiding in plain sight. The flyby effect is small, and for most space missions, it does not significantly alter their paths. But the fact that it exists at all suggests that there is still more to learn about the subtle forces acting on objects in space. The Silent Pioneers, the quest for elusive population 3 stars. The first stars in the universe are believed to have formed more than 13 billion years ago, yet none have ever been observed directly. These ancient stars, known as population 3 stars, are thought to have been vastly different from the stars we see today. Unlike modern stars, which contain heavier elements like carbon, oxygen, and iron, these first stars were made almost entirely of hydrogen and helium, the only elements present in the early universe. Because they contained no metals, they likely grew to enormous sizes, burned incredibly hot, and ended their lives in violent explosions that seeded the cosmos with the elements needed for later generations of stars and planets. The existence of population 3 stars is a fundamental prediction of cosmology. They are believed to be responsible for the first steps in the cosmic cycle of element formation, forging the heavier elements necessary for the development of galaxies, solar systems, and even life itself. Yet, despite decades of searching, astronomers have never found a single one. The challenge is that they likely existed only during the universe's earliest eras. They would have formed around a few 100 million years after the Big Bang, at a time when the first galaxies were just beginning to assemble. Unlike later stars, which can survive for billions of years, these early stars are thought to have been extremely short-lived. Because they were so massive, they would have burned through their nuclear fuel in just a few million years before exploding as supernovae. Any population 3 stars that once existed are long gone, leaving astronomers with only indirect ways of detecting their presence. One of the primary methods used to search for traces of these ancient stars is by looking deep into the universe with powerful telescopes. Because light takes time to travel, the farther we look, the further back in time we see. Telescopes like the James Webb Space Telescope, or JWST, have been scanning the skies for ancient galaxies that might contain clues about the existence of population 3 stars. Astronomers hope to find evidence of their light in the most distant galaxies, where the first stars and black holes were beginning to shape the cosmos. One way to identify population 3 stars is by analyzing the light coming from early galaxies. Since these stars would have been composed of only hydrogen and helium, they would have had a very specific spectral signature, lacking the heavy elements that are present in modern stars. By studying the light from the oldest galaxies, astronomers hope to find signs of stars with these unique characteristics. Another approach involves studying the chemical composition of the universe today. If population 3 stars once existed, they would have exploded in powerful supernovae, scattering heavier elements into space. By analyzing the chemical makeup of ancient gas clouds and the oldest known stars in the Milky Way, scientists can search for patterns that might indicate the influence of the very first stars. Some old stars in our galaxy, known as ultra-metal-poor stars, contain extremely low levels of heavy elements, suggesting that they may have been enriched by population 3 supernovae long ago. Some of the strongest evidence for population 3 stars comes from observations of distant quasars. The light from these quasars passes through ancient gas clouds on its way to Earth. Some of these clouds appear to have very low amounts of heavy elements, which could mean they were influenced by population 3 stars. The lack of direct observations of population 3 stars remains a mystery. Some scientists have proposed that these stars may not have been as massive as originally thought, meaning they could have survived longer and might still exist today in very remote parts of the universe. Others suggest that population 3 stars may have collapsed directly into black holes before exploding, making them even harder to detect. Another possibility is that the conditions needed to form these stars were rarer than expected. The early universe was a chaotic place, with galaxies colliding and black holes growing rapidly. If population 3 stars formed in very specific environments, they might have been much less common than originally believed. The search for these missing stars is a quest to uncover the origins of the elements that make up the universe. Every atom of carbon in our bodies, every molecule of oxygen we breathe, and every grain of iron in the Earth's core can be traced back to the nuclear reactions inside stars. Finding population 3 stars would provide the final piece of the puzzle, revealing how the first generation of stars set the stage for everything that followed. Stellar genesis, revisited, metallicity, and the birth of the first stars. In the modern universe, the birth of a star follows a well-understood process. Clouds of gas and dust collapse under their own gravity, forming dense cores that heat up until nuclear fusion ignites in their centers. The process is influenced by many factors, including the presence of heavy elements, what astronomers call metals. These metals, elements heavier than hydrogen and helium, play a crucial role in the cooling of gas clouds, helping them condense into new stars. However, in the early universe, before any metals had been created, the process of stellar formation must have worked in a very different way. Population 3 stars formed in an environment where the only available elements were hydrogen, helium, and a small trace of lithium. These elements came directly from the Big Bang and filled the universe in a hot, uniform state. Over time, tiny fluctuations in density allowed gas to start clumping together, eventually forming the first protogalaxies. Inside these regions, the first stars would have begun to take shape. Without metals, cooling was much less efficient in the early universe. In today's star-forming regions, heavy elements like carbon and oxygen help dissipate heat, allowing gas clouds to fragment into smaller pieces. This leads to the formation of a wide range of star sizes, from small sun-like stars to massive short-lived giants. But in the metal-free environment of the early universe, gas clouds couldn't cool as easily. This meant that instead of breaking apart into many smaller stars, they tended to form a few massive stars, possibly hundreds of times the mass of the Sun. Computer simulations suggest that early stars grew to be much larger than modern ones because of this lack of metals. Without the cooling effects of heavier elements, the gas remained hot for longer periods, delaying the collapse of smaller fragments and allowing massive clumps to form. Some estimates suggest that population 3 stars could have reached several hundred times the Sun's mass, with surface temperatures much higher than anything seen in today's universe. These stars would have been incredibly bright, emitting vast amounts of ultraviolet radiation. The first stars not only illuminated the darkness of the early universe, but also played a key role in shaping its evolution. Their powerful radiation ionized the surrounding hydrogen, breaking it apart into protons and electrons. This period, known as the Epoch of Reionization, transformed the universe from a mostly neutral gas into the ionized state we see today. One of the key challenges in understanding population 3 star formation is figuring out exactly how large they were. If they were truly as massive as some models suggest, they would have ended their lives in incredibly powerful supernovae, completely dispersing their material into space. This would have left behind no direct remnants, no neutron stars, no black holes, only the chemical elements they produced. However, if some population 3 stars were smaller, they might have survived longer, or even collapsed into black holes. The metallicity of the early universe also influences how these stars might have formed in different regions. Not all parts of the early universe were the same. Some areas had slightly higher densities of gas, while others were more isolated. The variation in conditions means that the first stars may not have all been extremely massive, but could have formed with a wider range of sizes, especially in regions where early star formation had already enriched the gas with small amounts of heavy elements. While the first generation were metal-free, their supernovae quickly seeded the surrounding gas with heavier elements. This means that by the time the next stars began forming, the universe was already changing. Some astronomers believe that a second wave of early stars, sometimes called population 2, 5 stars, may have formed with a mix of pristine and enriched gas, leading to slightly different properties than the original population 3 stars. Since population 3 stars would have produced far more powerful explosions than those seen later, some researchers believe that rare ultra-bright supernovae observed in the early universe may be the remnants of these first stellar giants. Unconventional black holes, anomalies in mass, spin, and behavior. Black holes are thought of as simple objects, defined only by their mass, spin, and charge. In theory, they should follow predictable patterns based on these properties, but real observations suggest that not all black holes behave as expected. Some defy the conventional rules, exhibiting unusual spins, masses, or interactions that challenge standard models. These anomalies force astronomers to rethink what black holes are and how they evolve. One of the biggest surprises has come from black hole mergers. In 2015, when LIGO detected the first confirmed gravitational waves, the source was a pair of merging black holes much more massive than expected. Before this discovery, most known black holes were either stellar mass black holes, which form from dying stars and typically range from a few to a few dozen times the Sun's mass, or supermassive black holes, which can reach millions or billions of solar masses and sit at the centers of galaxies. The black holes detected by LIGO, however, had masses of about 30 times the Sun's, far larger than typical stellar mass black holes, but nowhere near supermassive status. These detections raised important questions. How did such large black holes form? Were they the result of direct collapse, where massive stars bypass the supernova stage and collapse straight into black holes? Or did they grow through successive mergers, with smaller black holes combining over time? Some theories even suggest that these objects could be primordial black holes, ones that formed not from stars, but from density fluctuations in the early universe. Spin is another area where black holes don't always conform to expectations. Black holes gain spin when they form and through interactions with other objects, but their spins should generally align if they originate from the same system. Yet, observations of some merging black holes suggest that their spins are misaligned, with one or both spinning in a direction that doesn't match the orbital motion of the system. This suggests that at least some black holes are coming from chaotic environments, possibly formed in dense stellar clusters where they can be captured into binary systems rather than evolving together from a common progenitor star. Some black holes have been observed spinning at speeds near the theoretical limit. According to Einstein's equations, there is an upper boundary to how fast a black hole can spin before the physics around it starts to break down. This limit, known as the Kerr limit, is determined by the ratio between the black hole's spin and its mass. Some black holes seem to be pushing right up against this boundary, spinning so fast that space itself is being twisted and dragged around them in extreme ways. On the other end of the spectrum, some black holes appear to be spinning far slower than expected, or not at all. This is particularly odd in systems where a black hole is actively pulling in matter, since the process of accretion should transfer angular momentum and cause the black hole to spin faster. If a black hole isn't spinning much, it might mean that something in its history disrupted this process. One possibility is that some black holes form in highly energetic supernova explosions that eject mass in asymmetrical ways, leading to a lower net spin. Another puzzle comes from black holes that exist in mass ranges where they theoretically shouldn't. For example, there is something called the mass gap, a range of masses between about 50 and 120 times the Sun's mass, where black holes aren't expected to form through standard stellar evolution. This is because stars in this range undergo a process called pair instability supernova, where they explode so violently that no black hole is left behind. Yet, observations have revealed black holes right in this forbidden zone, suggesting that either our understanding of stellar explosions is incomplete, or that these black holes formed through different mechanisms, such as earlier mergers or direct collapse. At the opposite end, intermediate mass black holes, or IMB8s, are another enigma. While we know of stellar mass and supermassive black holes, IMB8s, those between about 100 and 100,000 solar masses, are strangely elusive. Theories suggest that IMB8s should exist, perhaps as the building blocks of supermassive black holes, but only a handful of potential candidates have been detected. One possible detection came from gravitational waves, where a merger appeared to create a black hole in this mass range. Other candidates have been identified in dense star clusters, or at the centers of dwarf galaxies. If IMB8s are real and common, they could be the missing link in understanding how black holes grow from stellar to supermassive scales. Even the nature of event horizons has been questioned. Some theoretical models suggest that exotic alternatives, like gravastars or fuzzballs, could mimic the appearance of black holes but lack true event horizons. In these scenarios, what we perceive as black holes might instead be strange objects where quantum effects prevent complete collapse. While there is no direct evidence for such alternatives yet, some anomalies in gravitational wave signals and observations of high-energy cosmic rays have led some researchers to consider the possibility. Black holes have always been mysterious, but these anomalies show that they are even stranger than we once thought. The more we observe, the more we find deviations that challenge our understanding of gravity, star formation, and the extreme physics of the universe. With new observatories, next-generation gravitational wave detectors, and improved high-energy observations, we are entering an era where these mysteries may finally be solved, or lead to even more questions. Microwave whispers, probing the anomalous emission from the Milky Way. The Milky Way is filled with radiation, stretching across the entire electromagnetic spectrum. From high-energy gamma rays to the long, gentle waves of radio signals, space is awash with emissions that scientists have studied for decades. Yet among the many expected signals, astronomers have noticed something strange: anomalous microwave emissions that don't match any standard predictions. Unlike other emissions, which are tied to well-understood sources like star-forming regions or the CMB, these microwaves seem to originate from interstellar dust in a way that doesn't align with established models. For a long time, dust has been known to absorb and re-emit energy at different wavelengths. But the strange microwave glow doesn't fit neatly into any of the expected patterns. When astronomers map the CMB, they must account for signals coming from within our own galaxy. The challenge is to separate the CMB from foreground emissions, such as synchrotron radiation from charged particles spiraling around magnetic fields, or thermal radiation from warm dust grains. However, when researchers tried to clean up the CMB data, they discovered an extra component in the microwave range, something unaccounted for by known emission sources. One of the earliest hints of this unexpected microwave glow came from the COBE satellite in the 1990s, followed by more precise observations from WMAP and Planck. The data showed a diffuse but noticeable emission at frequencies between 10 and 60 GHz, scattered throughout the Milky Way. The anomaly wasn't strong, but it was persistent, appearing in multiple regions of the galaxy where no clear source was expected. The first explanation considered was spinning dust grains, tiny particles that could be rapidly rotating due to interactions with interstellar radiation or magnetic fields. These grains, only nanometers in size, might act like miniature antennas, releasing microwave radiation as they spin. The idea seemed promising because small dust grains are abundant in the Milky Way and could theoretically account for the signal. However, while models of spinning dust have been refined over time, they don't fully explain the emission's distribution or intensity. Another possibility is that the anomalous microwaves are linked to unknown interactions between dust and cosmic rays. Cosmic rays collide with interstellar dust all the time. If these collisions excite the dust grains in an unexpected way, they could produce a faint but widespread microwave signal. Yet, no current model successfully ties cosmic ray interactions to the exact frequency range of the anomalous emission. The Milky Way's magnetic field is complex and extends across vast regions of space, interacting with charged particles and dust alike. Some researchers suggest that certain types of magnetized grains, possibly containing iron, could contribute to the strange microwave signature. If these grains align with the magnetic field and rotate in a specific way, they might emit microwaves that contribute to the overall anomaly. If the anomalous microwave emission were a universal process tied to interstellar dust, it should appear in distant galaxies as well. Some studies have hinted at similar emissions in other galaxies, but the signals are weak and difficult to separate from other sources. This raises the question of whether the phenomenon is unique to the Milky Way or simply harder to detect elsewhere. The Planck satellite provided some of the most detailed maps of the Milky Way's microwave emissions, helping astronomers refine their understanding of dust physics. Yet despite these advancements, no single model fully accounts for the observed anomalies. The emissions don't match traditional thermal radiation, nor do they fit neatly with known non-thermal processes. This leaves open the possibility that something fundamentally new is at play. An unknown property of interstellar dust, an unrecognized interaction in the galactic environment, or even a completely new astrophysical mechanism. One idea is that cosmic rays might be triggering exotic particle interactions. Certain types of hypothetical particles, such as axions, could decay into photons under specific conditions. If such a process were occurring throughout the Milky Way, it could produce a faint but detectable microwave signature. Axions are a theoretical particle proposed to explain dark matter, and some physicists have suggested that their interactions might be responsible for unexpected signals seen in astrophysical data. In quantum field theory, empty space is not truly empty. It is filled with virtual particles that pop in and out of existence. Certain models suggest that these fluctuations could create small but measurable energy emissions across large distances. If such quantum effects were producing microwaves in the interstellar medium, it could represent a new kind of physics not accounted for in standard models. Despite these alternative theories, many astrophysicists remain cautious about invoking new physics. Historically, unexplained signals in astronomy have often turned out to be caused by known but misunderstood processes rather than truly exotic phenomena. The history of cosmic discoveries is filled with examples where initial mysteries were eventually solved with better data and improved models. It is possible that the anomalous microwave emission will follow this pattern. Something ordinary, like a previously overlooked property of dust, could turn out to be the cause. Scientists simulate interstellar environments using vacuum chambers and laser-induced reactions, studying how particles absorb and emit radiation. Some experiments have successfully produced microwave-like emissions under certain conditions, suggesting that previously overlooked properties of dust could be responsible. However, the controlled conditions of a lab are far removed from the vast and complex environment of the galaxy. Translating these findings into a complete astrophysical explanation remains a challenge. Instruments, such as NASA's SPHERE-X mission, will map the sky in multiple wavelengths, potentially offering more clues about the composition of interstellar dust and its role in these unexplained emissions. While theories evolve and new data emerges, the whispers of unexplained microwaves persist, urging astronomers to keep listening. Magnetic mysteries. The role of cosmic magnetic fields in shaping the universe. Magnetic fields are everywhere in the universe. They thread through galaxies, stretch across intergalactic space, and influence the motion of charged particles. Despite their presence, cosmic magnetic fields remain one of the least understood forces shaping the cosmos. Unlike gravity, which dominates the large-scale structure of the universe, or dark matter, which has been the focus of many astrophysical studies, magnetic fields are often overlooked. Yet, they could be playing a fundamental role in everything from star formation to galaxy evolution. At a small scale, magnetic fields shape the environments around stars and planets. The Sun, for instance, has an incredibly complex and dynamic magnetic field, responsible for solar flares, sunspots, and the ejection of charged particles into space. Earth's own magnetic field shields the planet from harmful cosmic radiation, creating the auroras visible near the poles. These planetary and stellar fields are well documented, but when it comes to the larger cosmic picture, the role of magnetism is far less understood. On a galactic scale, observations have revealed that most galaxies, including our own Milky Way, are permeated by large-scale magnetic fields. These fields are weak compared to those on planets or stars, but they extend across vast distances. In the Milky Way, the magnetic field appears to follow the structure of the galaxy, aligning with the spiral arms. Similar patterns have been detected in other spiral galaxies, suggesting that magnetism is linked to their formation and evolution. But where do these cosmic magnetic fields come from? One possibility is that they originate from the early universe. In the moments following the Big Bang, the cosmos was a hot, dense plasma filled with charged particles. As the universe expanded, slight imbalances in this plasma could have generated weak seed magnetic fields. Over billions of years, these fields could have been amplified by processes like turbulence and the motion of interstellar gas, leading to the large-scale fields seen today. Another possibility is that magnetic fields are constantly being generated and strengthened within galaxies themselves. The movement of ionized gas in a rotating galaxy can act like a dynamo, continuously amplifying existing magnetic fields. This dynamo effect could explain how galaxies maintain their magnetic structures over cosmic time. However, it is still unclear whether this process alone can account for the observed strength of galactic fields, or if another mechanism is at play. As galaxies interact and collide, their magnetic fields could shape the movement of gas, influencing where new stars form. Observations of galaxy clusters, huge collections of galaxies bound together by gravity, suggest that magnetic fields may even affect the large-scale structure of the universe. Some studies indicate that filaments of the cosmic web could be magnetized. If true, this could change our understanding of how matter moves through intergalactic space. Jets of high-energy particles ejected from supermassive black holes appear to be controlled, at least in part, by powerful magnetic fields. These jets, extending for thousands or even millions of light years, are thought to be shaped by the twisting and stretching of magnetic field lines near the black hole. Understanding how these magnetic forces interact with gravity and plasma could provide new insights into the environments around black holes and the formation of quasars. Unlike visible light or radio waves, magnetic fields cannot be observed directly. Instead, astronomers rely on indirect methods to study them. One technique involves measuring the polarization of light as it passes through magnetized regions of space. This can reveal the direction and strength of magnetic fields along the line of sight. Another method involves studying the motion of charged particles, which tend to spiral around magnetic field lines. By analyzing how cosmic rays move through space, scientists can infer the presence of magnetic fields. One of the biggest remaining questions is how magnetic fields interact with dark matter and dark energy. If dark matter is made up of charged particles, then it could be influenced by cosmic magnetism in ways we do not yet understand. Some theories even suggest that magnetic fields could have played a role in shaping the structure of dark matter in the early universe. Time's relativity, extreme time dilation, and cosmic chronology, challenges. In everyday life, time appears to move forward at the same steady pace no matter where we are. But when we move at high speeds or enter strong gravitational fields, time behaves differently. It stretches, slows, and warps in ways that defy intuition. This phenomenon, known as time dilation, is one of the most fascinating predictions of Einstein's theory of relativity, and it plays a crucial role in understanding the broader chronology of the universe. As an object gets closer to a black hole's event horizon, the gravitational field becomes so strong that time slows down dramatically for anything near it. A person falling toward the event horizon would experience time normally from their own perspective, but to an observer watching from a safe distance, their movement would appear to slow down more and more. At the edge of the event horizon, time would appear to freeze entirely from the outside viewer's standpoint. Does an object ever truly cross the event horizon from an external observer's perspective, or does it remain suspended in time? In practical terms, the infalling object would still cross over, but the way its light signals stretch and fade makes it seem as if time stops at the boundary. This kind of extreme time distortion changes the way we think about events near black holes, and even how we define past, present, and future in such environments. Time dilation also occurs when objects travel at speeds approaching the speed of light. According to special relativity, the faster an object moves, the slower time passes for it relative to a stationary observer. This effect has been tested in experiments with atomic clocks placed on fast-moving jets or satellites. The moving clocks tick slightly slower than those on Earth, confirming Einstein's predictions. The GPS system that powers navigation on Earth has to account for both gravitational time dilation and the effects of speed on satellite clocks. Without these corrections, GPS signals would quickly drift out of sync, making navigation unreliable. If a spacecraft were to reach a significant fraction of the speed of light, time would pass more slowly for those on board compared to people remaining on Earth. A journey that might seem to last only a few years for the crew could correspond to decades or centuries passing for those left behind. This leads to the so-called twin paradox, where one twin who travels at high speeds returns much younger than their sibling who stayed on Earth. When we look at distant galaxies, we are seeing them as they were in the past because of the time it takes for their light to reach us. But the farther away a galaxy is, the more its light is redshifted due to the expansion of the universe. This redshift isn't just a measure of distance, it's also a measure of time dilation on a grand scale. In the early universe, when everything was much denser, time may have flowed differently compared to how it does today. Some cosmologists have even suggested that in the earliest moments after the Big Bang, time itself could have emerged in a different way than we currently understand. Some theories propose that time is not a fundamental property of reality, but emerges from deeper physical principles. Quantum mechanics suggests that time might behave differently at microscopic scales, where particles can exist in superpositions and states can become entangled in ways that don't follow our usual experience of time's progression. There is speculation that what we perceive as time could be a consequence of quantum processes rather than an independent entity. Other theories question whether time is truly one-directional. In everyday life, time seems to flow from past to future, driven by the increase of entropy, the tendency of things to become more disordered over time. But in the equations of physics, time is often symmetric, meaning there's no fundamental reason why it couldn't run backward under certain conditions. Some cosmologists have proposed that another universe, mirroring our own but running in reverse, could exist on the other side of the Big Bang. When astronomers study quasars, They noticed that their light fluctuations appear to happen at slower rates than expected. Some researchers believe this is another effect of time dilation, as these objects existed when the universe was younger and expanding more rapidly. Neutrino enigmas, the ghostly messengers of the cosmos. Neutrinos are tiny, nearly massless particles travel through space, passing through matter with little to no interaction. They are produced in a variety of cosmic events, but despite their abundance, they are incredibly difficult to detect. Neutrinos are produced in vast quantities during stellar processes, including in the hearts of stars like our Sun, in supernovae, and even in the early moments of the universe. Yet, because they rarely interact with anything, they escape detection by most conventional means. A neutrino can pass through an entire planet without ever being noticed. This property is both their most intriguing feature and the source of many of the challenges that physicists face when studying them. These particles are neutral, meaning they do not carry an electrical charge, and they interact with matter only through the weak nuclear force, one of the four fundamental forces in nature. Unlike electrons or protons, which interact through electromagnetic forces and can be easily detected, neutrinos almost never interact with atoms. Their weak interaction with matter makes them incredibly hard to catch, and as a result, they can travel vast distances across the universe without any significant slowing down or deflection. This ability to travel unimpeded through space allows them to carry information from distant cosmic events, offering a unique window into the most extreme and energetic processes of the universe. The Sun is the most well-known source of neutrinos. It generates a constant stream of these particles through nuclear fusion. Every second, billions of neutrinos pass through our bodies, Earth, and even our planet's core. Detecting these solar neutrinos was one of the first major achievements in neutrino science, and it provided crucial evidence for the processes taking place inside our Sun. However, the real excitement about neutrinos comes from the more violent events in the cosmos, where they are produced in far greater numbers and at much higher energies. When a massive star runs out of fuel and collapses under its own gravity, it can result in a supernova explosion that ejects a large portion of the star's mass into space. These explosions produce a tremendous number of neutrinos, which escape almost immediately from the core of the star and carry with them critical information about the processes taking place during the explosion. Studying these neutrinos can give astronomers a glimpse into the inner workings of these catastrophic events, providing data that is not accessible through visible light or other forms of radiation. In fact, neutrinos played a crucial role in understanding supernova 1987A, one of the most well-studied supernovae in history. For the first time, scientists detected a burst of neutrinos just hours before the visible light from the explosion reached Earth. This was a groundbreaking discovery, as it allowed scientists to study the early stages of the supernova's explosion. The neutrinos provided valuable insights into the mechanisms behind stellar collapse, including the role of neutrinos in the explosion process itself. The event confirmed the idea that neutrinos are central to the dynamics of a supernova, helping to drive the shockwave that propels the outer layers of the star into space. Another cosmic event that produces large numbers of neutrinos is the collision of neutron stars. These collisions, which occur when two neutron stars spiral inward and merge, release an enormous amount of energy in the form of both gravitational waves and electromagnetic radiation. Neutrinos are also produced in these violent mergers, offering yet another potential way to study the most extreme environments in the universe. Neutrinos are fundamental to our understanding of particle physics, as their strange properties challenge many aspects of the Standard Model. For instance, neutrinos have mass, but their mass is so small that it is nearly impossible to detect directly. This discovery of neutrino mass was one of the key pieces of evidence that led to the theory of neutrino oscillation, where neutrinos change flavor as they travel through space. This phenomenon, observed in experiments such as those at Japan's Super Kamiokande detector, showed that neutrinos can oscillate between different types or flavors, a behavior that defies the predictions of the Standard Model. and implies that neutrinos have a non-zero mass. Just as the CMB provides a snapshot of the early universe, the neutrino background offers information about the state of the universe at an even earlier time. Neutrinos produced in the first few seconds of the universe's existence permeate all of space, but detecting them remains an immense challenge because they are so weakly interacting. As neutrinos travel unimpeded through space, they carry with them information from the distant past. The facilities that are currently used to study neutrinos are often massive and located deep underground or in large volumes of water to shield them from other types of radiation. One of the most advanced detectors in the world is the IceCube Neutrino Observatory, located at the South Pole. IceCube is a vast array of sensors embedded deep in the Antarctic ice, capable of detecting the faintest traces of neutrinos that interact with the ice. By studying the patterns of light produced when neutrinos collide with the ice, scientists can determine the direction and energy of the incoming particle. Neutrinos offer a rare opportunity to peer into some of the most violent and distant phenomena in the cosmos. Despite their elusiveness, these particles may very well hold the key to understanding the universe's most fascinating events. Gamma-ray surprises, unexplained emissions from the galactic center. At the heart of the galactic center of the Milky Way lies a supermassive black hole known as Sagittarius A*, which exerts an immense gravitational pull on the stars, gas and dust surrounding it. Yet, while much of our understanding of this region comes from studying the effects of the black hole and the high-energy processes it causes, recent discoveries of unexpected gamma-ray emissions have added a layer of complexity to our view of this enigmatic part of the sky. Gamma rays, the highest energy form of electromagnetic radiation, are produced by some of the most energetic processes in the universe. They are the result of high-energy interactions between particles, such as those that occur in supernova remnants, active galactic nuclei, and the regions surrounding black holes. In the case of the galactic center, gamma rays are expected to originate from interactions involving the supermassive black hole and the surrounding matter. However, the gamma-ray emissions detected in this region go far beyond what scientists initially predicted, suggesting that there may be processes at work that are not fully understood. The mystery began in 2009, when the Fermi Gamma-Ray Space Telescope, an observatory dedicated to detecting gamma rays from across the universe, began to observe unexpected and intense gamma-ray emissions coming from the direction of the galactic center. These emissions were not directly tied to known sources of gamma rays in the region, such as the supermassive black hole or the superheated gas swirling around it. Instead, they appeared to come from an area extending far beyond the immediate vicinity of the black hole, suggesting the presence of a much larger, more diffuse source of high-energy particles. This discovery raised a host of questions about what could be responsible for these unusual emissions. Are they coming from an unknown source of high-energy particles? Could they be the result of an undiscovered astrophysical phenomenon? One leading hypothesis is that the gamma rays could be the result of the annihilation of dark matter particles. Dark matter is believed to be concentrated in the dense regions of galaxies, including the galactic center. If dark matter is made up of particles that can annihilate each other, this process could produce gamma rays as a byproduct. The fact that the gamma-ray emissions from the galactic center are diffuse and spread across a large area fits well with this idea. If dark matter is indeed interacting and annihilating, it could explain the unexpected gamma-ray signature. Another possible explanation for these mysterious gamma-ray emissions involves the cosmic rays that fill the galactic center. When cosmic rays collide with gas clouds or other matter, they can produce gamma rays. The dense environment around the supermassive black hole could provide an abundant source of cosmic rays, which may interact with the surrounding material to produce the observed gamma radiation. However, this theory still doesn't fully explain the wide-ranging and consistent nature of the emissions, which suggests that cosmic ray interactions alone may not be the full story. Some have proposed that the emissions could be the result of a previously unknown astrophysical object or process. For example, a hypothetical class of compact objects known as dark matter clumps could be interacting in the galactic center, producing high-energy particles that emit gamma radiation. Alternatively, a new class of energetic pulsars or microquasars could be contributing to the gamma-ray flux, though such objects have yet to be detected in this region. The Milky Way's galactic center is surrounded by vast clouds of gas and dust, and these clouds could play a crucial role in the production and distribution of gamma rays. The interactions between high-energy particles and this interstellar material could amplify the gamma-ray signal, creating a more diffuse emission than would be expected from a point source like the supermassive black hole. As more data is collected and more sophisticated models are developed, scientists are hopeful that they will eventually be able to unlock the secrets of this galactic enigma. The answers to these questions could reveal hidden processes and forces that govern the behavior of the cosmos at the most extreme scales. Rethinking inflation. Alternative scenarios for the universe's birth. The idea of cosmic inflation proposes that, in the first fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion, stretching space itself at an unimaginable speed. This concept helps explain many of the large-scale features of the cosmos, from the uniformity of the CMB to the distribution of galaxies. However, despite its successes, inflation is not the only possible explanation for the universe's birth. One of the motivations for exploring alternatives to inflation is the idea that it might not be the final answer to the mysteries of the early universe. Inflation was first proposed in the 1980s to solve key problems in cosmology, such as why the universe appears so smooth on large scales, and why its structure does not seem random. The idea that space expanded exponentially in an instant seemed to provide a perfect solution. However, inflation itself relies on certain assumptions, such as the existence of an unknown energy field called the inflaton, that remain purely theoretical. Without direct evidence of an inflaton particle or field, some physicists argue that other models should be explored. Instead of originating from a single explosive event, the cyclic universe model suggests that the universe has undergone endless cycles of expansion and contraction. In this view, what we think of as the Big Bang might have been just one phase in an ongoing sequence of cosmic rebirths. Some versions of this theory suggest that each cycle begins when the universe contracts into an extremely dense state, followed by a new expansion phase. Others propose that quantum fluctuations, or unknown physics, could prevent a full collapse, instead leading to a slow rebound. In traditional inflation, the smoothness of the cosmos is explained by the rapid stretching of space. But in a cyclic universe, the uniformity could instead arise naturally over repeated cycles, as any irregularities get smoothed out over immense stretches of time. This scenario removes the need for an inflaton field and suggests that space and time may be eternal, with no true beginning. Some models propose that the early universe was not a singularity, but instead emerged from a pre-existing state. One such idea is the emergent universe scenario, which suggests that the cosmos existed in a stable, eternal phase before transitioning into a rapid expansion. In this view, the universe did not have a single moment of birth, but rather evolved from a prior state that was governed by unknown physics. Some versions of this theory propose that quantum effects could have allowed the universe to slowly grow until reaching a critical point, at which it underwent a phase transition into rapid expansion. Quantum mechanics itself offers other intriguing possibilities. Some researchers suggest that the universe could have originated from a quantum fluctuation in a vacuum. In this scenario, space and time themselves are not fundamental, but arise from deeper principles of quantum physics. The idea that the universe could emerge from nothing might seem counterintuitive, but in quantum mechanics, particles can briefly pop in and out of existence due to fluctuations at the smallest scales. Some theories extend this idea to the entire cosmos, proposing that the Big Bang was itself a quantum event. Some theories propose that gravity behaved differently in the early universe, leading to an expansion that mimicked inflation, but arose from a different cause. One such model suggests that the laws of gravity changed as the universe transitioned from a high-energy state to a lower-energy one, naturally leading to rapid growth. If true, this could mean that inflation is not needed at all, and that the universe's early expansion was driven by a more fundamental shift in the fabric of space-time. In some models, inflation does not occur everywhere, but is instead a local phenomenon in certain regions of a vast cosmic landscape. If this idea is correct, our observable universe may be just one small pocket within a much larger structure, where different types of physics play out in other regions. This concept is difficult to test, but it suggests that what we consider the beginning of the universe might be just one event within a much grander framework. While inflation remains the dominant explanation, these alternative ideas show that cosmology is still an evolving field. Observations of large-scale structure and distant galaxies will continue to test different models, potentially revealing new clues about the true origins of space and time. Scientists remain open to the idea that inflation may one day be replaced by a deeper understanding of the cosmos, one that could redefine our understanding of the universe's origin. Cosmic strings and topological defects. Traces from the early universe. In the vast expanse of the cosmos, some of the most intriguing remnants of the early universe may not be found in the light of distant galaxies or the radiation left over from the Big Bang. Instead, they may exist as invisible but powerful structures woven into the very fabric of space itself. These hypothetical objects, known as topological defects, are thought to be relics from the first moments of cosmic history, structures that formed as the universe transitioned from one state to another in its infancy. Cosmic strings are not ordinary physical objects, but rather defects in space-time itself, akin to cracks that form when ice freezes. The idea behind them comes from physics theories that describe the universe undergoing phase transitions, much like water turning to ice or metal becoming magnetized. In the extremely hot, dense environment of the early universe, the fundamental forces of nature may not have always been separate as they are today. As the universe expanded and cooled, these forces are believed to have split from a single unified state into the distinct forces we recognize now: gravity, electromagnetism, and the strong and weak nuclear forces. During this process, imperfections could have formed, leaving behind narrow, immensely dense regions of space known as cosmic strings. A cosmic string, if it exists, would be incredibly thin, thinner than a proton, but extraordinarily massive, with just a single kilometer of string weighing as much as an entire planet. Unlike regular matter, these strings would not consist of particles, but would instead be disruptions in space-time itself, carrying an enormous amount of energy. Because of this, they could act as sources of intense gravitational effects, warping light and even influencing the movement of galaxies. One of the ways scientists hope to detect cosmic strings is through their impact on light from distant objects. If a cosmic string were to pass between Earth and a distant galaxy, it could create gravitational lensing, unlike the smooth curved bending of light seen with massive galaxies or black holes. A cosmic string would produce an abrupt duplication of the background object, splitting an image into two perfect, identical copies rather than distorting it into arcs. Astronomers have searched for such telltale signs in deep space surveys, though no confirmed detections have yet been made. Beyond cosmic strings, other topological defects could also exist as remnants of the early universe. One example is domain walls, two-dimensional sheets where regions of space with different properties meet. If the universe cooled unevenly in its early stages, different regions might have settled into slightly different physical states, forming vast boundary surfaces between them. Domain walls could stretch across immense cosmic distances, dividing space into different zones with unique fundamental properties. Another possibility is monopolies, theoretical particles predicted by certain extensions of physics. Unlike regular magnets, which have both north and south poles, a monopole would possess only a single magnetic pole, either north or south. Some theories suggest that these exotic particles should have formed in the high-energy environment of the early universe. However, despite extensive searches, no monopoles have been found, leading scientists to wonder if something prevented their formation, or if they were somehow diluted by cosmic expansion. Some early theories proposed that the distribution of galaxies might have been influenced by a network of cosmic strings stretching across space. As these strings oscillated and interacted with matter, they could have seeded the formation of clusters and filaments seen in today's cosmic web. However, current observations suggest that cosmic inflation, rather than cosmic strings, was the dominant force shaping the large-scale structure, leading to a decline in this theory's popularity. Despite the challenges in detecting these elusive structures, scientists continue to search for signs of their existence. Advanced gravitational wave detectors could potentially pick up disturbances caused by cosmic strings snapping or vibrating as they release bursts of energy. Additionally, high-energy cosmic rays or unusual patterns in the CMB could provide indirect evidence of topological defects. Baryogenesis and beyond. The puzzle of matter-antimatter. Imbalance. In the earliest moments of the universe, a perfect symmetry should have existed between matter and antimatter. According to our best theories, every particle of matter should have been created alongside its exact opposite, an antiparticle with the same mass but opposite charge. If the universe had followed the most basic physical principles, these pairs would have annihilated each other completely, leaving nothing but a vast sea of energy. And yet, when we look around, we see a universe filled with stars, planets, and galaxies made entirely of matter. Antimatter, apart from tiny amounts found in cosmic rays or produced in high-energy experiments, is nowhere to be seen. This fundamental imbalance, known as the matter-antimatter asymmetry, remains one of the most profound mysteries in cosmology. Scientists believe that at some point in the early universe, a process called baryogenesis must have tipped the scales in favor of matter. The term baryon refers to particles like protons and neutrons, which make up the bulk of ordinary matter. Baryogenesis refers to the unknown mechanism that led to a tiny excess of baryons over antibaryons, allowing some matter to survive while the rest annihilated away. The exact cause of this imbalance remains elusive, but physicists have outlined several possible conditions that could have allowed it to happen. For matter to have won out, certain physical laws must have been broken in the early universe. One of the key conditions is a violation of what is known as charge parity, or CP, symmetry. CP symmetry states that the laws of physics should apply equally to particles and their antiparticles when their charges and spatial orientations are reversed. However, experiments have shown that some particles, such as certain mesons, do exhibit slight CP violations, meaning they decay in a way that slightly favors matter over antimatter. But the observed CP violations are far too weak to explain the vast matter-antimatter asymmetry we see in the universe, meaning some other, stronger violation must have occurred in the early cosmos. Another necessary ingredient for baryogenesis is that the universe must have been out of thermal equilibrium at some point. In simple terms, this means that conditions had to be changing rapidly, such as during cosmic inflation or a phase transition, so that certain reactions could occur more often in one direction than the other. If the universe had remained in perfect equilibrium, matter and antimatter would have continued forming and annihilating in equal amounts, with no net gain for either. Several theories have been proposed to explain how these conditions might have been met. One of the leading ideas involves a process called electroweak baryogenesis, which suggests that the imbalance may have arisen during the electroweak phase transition. the moment when the electromagnetic and weak nuclear forces separated in the early universe. If this transition was not smooth, but rather happened in a way that allowed temporary pockets of CP violation, it could have favored the production of more baryons than antibaryons. However, for this theory to work, the Higgs boson, the particle associated with the Higgs field, which gives other particles mass, would need to have different properties than what we currently observe. Another idea, known as leptogenesis, suggests that the asymmetry might have first appeared in neutrinos. In this scenario, certain heavy neutrinos that existed in the early universe could have decayed in a way that slightly favored matter over antimatter. This tiny imbalance in the neutrino sector could then have been transferred to baryons through particle interactions, ultimately leading to the dominance of matter. Experiments at particle colliders like the LHC are working to measure CP-violating processes more precisely, looking for hints of unknown interactions that could explain the imbalance. Apart from that, any asymmetries in the earliest distribution of matter and antimatter might have left subtle imprints on the CMB. Astronomers are also searching for traces of antimatter in cosmic rays or distant galaxies. If large regions of antimatter existed somewhere in the universe, we would expect to see powerful annihilation events where matter and antimatter collide, producing distinctive bursts of gamma rays. However, no such signals have been detected, reinforcing the idea that matter vastly outnumbers antimatter on cosmic scales. Ghostly galaxies, the enigma of ultra-diffuse structures. At first glance, ultra-diffuse galaxies look like faint smudges of light, barely visible even through powerful telescopes. They can be as large as the Milky Way, yet they contain only a fraction of its stars. Some are almost entirely made of dark matter, while others seem to be missing it altogether. These ghostly structures sit at the fringes of conventional astrophysics, forcing researchers to rethink the very definition of a galaxy. The discovery of ultra-diffuse galaxies, or UDGs, happened almost by accident. In 2015, astronomers scanning the Coma cluster, a collection of galaxies 300 million light-years away, found something unexpected: dozens of extremely faint objects scattered throughout the cluster. These galaxies had sizes comparable to the Milky Way, but contained so few stars that they were nearly invisible. Their diffuse nature made them easy to overlook in past surveys, and yet they were everywhere. As scientists expanded their search, they realized that UDGs weren't just confined to galaxy clusters. They existed in a variety of environments, from the edges of the cosmic web to the vast emptiness of intergalactic space. One of the biggest mysteries surrounding UDGs is how they can be so large while remaining so faint. Traditional galaxy formation models suggest that galaxies grow by accumulating gas and forming stars. Yet UDGs appear to have undergone very little star formation. Some theories propose that these galaxies were once normal, but some event, perhaps a violent interaction with another galaxy or powerful bursts of supernovae, stripped them of their star-forming material. Others suggest that they formed in dark matter halos that were unable to pull in enough gas to create bright, star-filled galaxies. Some of the most baffling UDGs appear to defy expectations when it comes to dark matter. One such galaxy, known as DF2, seemed to have almost no dark matter at all. Dark matter is thought to be the invisible framework that holds galaxies together. Without dark matter, a galaxy's stars should fly apart due to their own motions. Yet, DF2 appeared stable, as if some unknown force was keeping it intact. On the opposite end of the spectrum, another UDG known as Dragonfly 44 seemed to be made almost entirely of dark matter. It had very few stars, but its total mass suggested that dark matter outweighed visible matter by a factor of at least 100. If dark matter is supposed to behave in a predictable way, why would some galaxies have almost none, while others are completely dominated by it? Many UDGs are found in dense galaxy clusters, where interactions between galaxies are common. Some scientists suspect that UDGs might have started as normal galaxies but were transformed by the harsh environment of the cluster. If a galaxy passes too close to a massive neighbor, it can have its gas stripped away, preventing new stars from forming. This process, known as ram pressure stripping, could explain why some UDGs are so faint. However, this doesn't explain why ultra-diffuse galaxies also appear in more isolated regions of space, far from the gravitational influence of larger galaxies. If UDGs form naturally in different environments, then their origins must involve more than just interactions with other galaxies. Unlike normal galaxies, which typically have a well-defined central bulge or disk, many UDGs lack clear organization. Their stars are spread thinly across enormous regions, making them more vulnerable to external forces. Some scientists believe that UDGs formed in low-density dark matter halos, which provided just enough gravitational pull to hold them together, but not enough to trigger the rapid collapse of gas into stars. Others suggest that powerful bursts of star formation in their early history could have blown much of their gas away, leaving behind an oversized star-poor remnant. They don't emit much light, which makes it difficult to measure their properties. Even with advanced telescopes, many UDGs remain hidden in the depths of space. Future telescopes, such as the Vera C. Rubin Observatory, will help uncover more of these elusive galaxies, possibly revealing whether they are a common but overlooked feature of the universe. If UDGs are more widespread than previously thought, they could have major implications for our understanding of galaxy formation. For decades, astronomers have built models assuming that galaxies follow predictable patterns of growth, structure, and dark matter content. UDGs suggest that nature may be far more diverse. If some galaxies can exist with hardly any dark matter, while others contain almost nothing but dark matter, then the very rules governing how galaxies form may need to be reconsidered. UDGs that lack dark matter offer a rare opportunity to study how galaxies behave in its absence. There is also a connection between UDGs and another cosmic mystery, the missing satellite problem. Standard dark matter theories predict that large galaxies like the Milky Way should have far more small satellite galaxies than we actually observe. Some researchers wonder if UDGs could be a missing piece of this puzzle. If many dwarf galaxies evolved into ultra-diffuse galaxies over time, they might explain why so few bright satellites are visible around massive galaxies. Instead of being completely absent, the predicted satellites might simply be too faint to detect using traditional methods. Challenging constants. Are nature's numbers truly universal? The universe appears to be governed by a set of fundamental constants, numbers that do not change, no matter where or when they are measured. These values define the behavior of everything from subatomic particles to the expansion of the cosmos. The speed of light, the charge of an electron, and the gravitational constant are all considered absolute, forming the foundation of physics as we understand it. If these constants were different, the universe itself would be unrecognizable. Atoms might not form, stars might never ignite, and life as we know it would be impossible. But what if these numbers are not truly fixed? What if the very foundations of physics are shifting across space and time? Modern physics assumes that these numbers are woven into the fabric of reality, but some observations suggest otherwise. One of the earliest challenges to the idea of fixed constants came from studies of the fine structure constant, a value that determines the strength of electromagnetic interactions. This number governs how light and matter interact and is crucial in defining the structure of atoms. Some astronomical observations hint that this constant might not be the same everywhere in the universe. Light from distant quasars, some of the oldest objects in existence, has shown slight deviations in how it interacts with surrounding gas clouds. If these variations are real, it could mean that the laws of physics are not uniform across the cosmos. Other investigations focus on whether constants have evolved over time. The gravitational constant, which determines the strength of gravity, has been tested against ancient celestial movements. Some researchers have examined the orbits of planets and the behavior of distant stars to see if gravity was weaker or stronger billions of years ago. While no conclusive evidence has been found, even the smallest change in gravity over time would have profound consequences. A slightly stronger gravitational force in the early universe could have accelerated the formation of galaxies, while a weaker force might have led to a more diffuse cosmos. The speed of light is another number often thought to be immutable. It acts as a cosmic speed limit, governing how fast information and energy can travel. But some speculative theories suggest that the speed of light might have been different earlier in the life of the universe. If true, this could solve certain cosmological puzzles, such as why distant regions of space appear so similar despite not having had time to exchange information. If light traveled faster billions of years ago, it could explain how the universe achieved its large-scale uniformity. To test whether constants are changing, scientists look to the past. One method involves analyzing the spectral lines of ancient stars. If a fundamental constant like the fine structure constant had changed over time, the positions of these spectral lines would shift. By comparing the light from modern stars with that of stars billions of years old, researchers can search for any tiny differences that could indicate a change in nature's numbers. Another approach involves studying atomic clocks, some of the most precise instruments ever built. These clocks rely on the natural vibrations of atoms to measure time with incredible accuracy. If any fundamental constant, such as the strength of the electromagnetic force, were to shift even slightly, it would cause a detectable change in how these clocks tick. By comparing multiple atomic clocks over long periods, scientists can look for tiny fluctuations that might reveal whether the constants are truly constant. Theories beyond the standard model of particle physics, such as string theory, suggest that what we think of as fixed numbers might emerge from more fundamental properties of space itself. In such models, changes in these constants might be linked to the way extra dimensions of space unfold or interact with our observable universe. If any of these constants do change, even slightly, it could force physicists to rethink many aspects of fundamental science. Some of the most precisely tested theories, such as quantum electrodynamics, rely on the assumption that these values do not fluctuate. A variation in a constant could mean that new physics is waiting to be uncovered, perhaps a deeper layer of reality that connects gravity, electromagnetism, and the quantum world in ways not yet understood. Phantom dimensions, unveiling hidden realms beyond perception. The world we experience is built upon 3 dimensions of space and 1 of time. Every object, every movement, every force we encounter follows the familiar framework of length, width, and height, evolving through the 4th dimension of time. But what if there are more, hidden layers of reality that exist beyond our perception, influencing the universe in ways we have yet to understand? In modern physics, the possibility of additional spatial dimensions is a serious subject of study. One of the strongest motivations for considering extra dimensions comes from string theory, a framework that attempts to unify all known forces of nature. In its most basic form, string theory proposes that the fundamental particles we observe are not point-like, as described in conventional physics, but instead tiny vibrating strings. These strings, incredibly small and energetic, can only function properly if they move through a universe that contains more than the familiar 3 spatial dimensions. Depending on the version of the theory, there could be up to 11 dimensions, each playing a role in shaping the universe's fundamental laws. If these extra dimensions exist, why do we not see them? One explanation is that they are compactified, meaning they are curled up on themselves at scales so small that they evade direct detection. Imagine a tightrope stretched across a canyon. To a person walking on the rope, movement appears to be limited to a single direction, forward or backward. But to an ant crawling along the rope's surface, an extra degree of freedom exists. It can move around the circumference of the rope. Similarly, extra dimensions could be wrapped up in such a way that they remain inaccessible to us, influencing physics in subtle but profound ways. Gravity is by far the weakest of the known fundamental forces. A small magnet can lift a paperclip against the entire gravitational pull of the Earth. This weakness has puzzled scientists for decades, and some have speculated that gravity's apparent feebleness might be an illusion. If gravity is capable of extending into extra dimensions while the other forces remain confined to three-dimensional space, it could explain why we perceive it as so weak. In this scenario, the missing strength of gravity is simply leaking into higher dimensional space, making it less noticeable in our own. Some models even suggest that our entire universe could be a three-dimensional brain, or membrane, floating within a higher dimensional space, much like a soap bubble drifting through the air. In this view, all known matter and forces are stuck to the surface of our three-dimensional universe, unable to escape into the extra dimensions, except for gravity, which spreads out more freely. If this is true, then there could be other three-dimensional brains parallel to our own, hidden just beyond our reach. Entire other universes could exist just a fraction of a millimeter away from us, separated only by an imperceptible higher dimensional gap. Some theories predict that extra dimensions could allow the creation of microscopic black holes in particle accelerators. These tiny black holes would evaporate almost instantly, leaving behind a specific pattern of decay products that scientists could detect. So far, no such evidence has been found, but experiments continue to push the boundaries of what can be observed. If gravity is indeed spreading into higher dimensions, its effects might be visible on cosmic scales. Some researchers suggest that dark matter could be a sign of interactions with higher dimensional space. If extra dimensions influence the way galaxies form and rotate, they might help explain why dark matter behaves so differently from ordinary matter. Some scientists have explored the possibility that consciousness itself could be linked to higher dimensional processes, though there is little evidence to support this idea. Others have proposed that wormholes, hypothetical tunnels through space-time, might be easier to form in a universe with extra dimensions, potentially allowing for shortcuts between distant points in space. If extra dimensions do exist, they may be the missing piece in our understanding of dark energy, the expansion of the cosmos, or even the nature of time itself. But for now, they remain just out of reach, an unseen layer of reality that hints at a universe far stranger and more intricate than we ever perceived. Time's labyrinth, temporal anomalies, and the possibility of cosmic time travel. Time moves forward, never backward, and shapes every moment of our existence. But the more scientists study it, the more they find that time is not as simple as it seems. It bends, stretches, and even slows down under the right conditions. It can be distorted by speed, gravity, and possibly even the structure of the universe itself. These strange behaviors raise an intriguing question. Is time travel, moving through time in ways beyond our everyday experience, actually possible? According to special relativity, time moves slower for an object traveling at high speeds. While this time dilation effect is small at everyday speeds, it becomes dramatic as objects approach the speed of light. This means that, in a way, high-speed travel could allow someone to move forward in time at a different rate than those they leave behind. The stronger the gravitational pull, the slower time moves. A person orbiting close to a black hole, for example, could experience time passing at a fraction of the rate compared to someone far away. If they spent just a few hours in this orbit and then returned to a distant observer, they might find that years or even centuries had passed elsewhere. If time can stretch and slow down, could it also be reversed? The laws of physics, as they are currently understood, allow for solutions where time could, in theory, loop back on itself. One of the most famous concepts for time travel is the idea of a closed time-like curve, a theoretical path in space-time that loops back to its own past. If such a curve existed, an object or person could follow it and arrive at an earlier point in time. Some solutions to Einstein's equations suggest that massive rotating objects might naturally twist spacetime in such a way that time travel could become possible. This has led to speculation about whether enormous spinning black holes, or even entire rotating galaxies, might contain the conditions needed for time loops. Some researchers have proposed that wormholes could also be used for time travel. If a wormhole connected two distant points in space and one end of it experienced stronger gravitational time dilation than the other, then stepping through it could allow a traveler to emerge at a different moment in time. However, wormholes, if they exist, might be unstable and collapse too quickly to be useful. Even if they could be stabilized, they would likely require exotic forms of matter with negative energy, something that has never been observed in large enough amounts. Some theories suggest that if two cosmic strings passed close to one another while moving at nearly the speed of light, they could create a space-time configuration that permits time travel. But like wormholes, these structures remain purely theoretical. While time travel into the future is a natural consequence of relativity, traveling to the past raises deeper problems. The most famous of these is the grandfather paradox, which questions what would happen if someone traveled back in time and changed an event that led to their own existence, like preventing their grandfather from meeting their grandmother. If they succeeded, then they would never have been born, and if they were never born, they could not have traveled back in time in the first place. Some physicists believe that paradoxes like this make time travel to the past impossible. Others suggest that the universe may correct itself to prevent such contradictions, or that traveling to the past would create an alternate timeline rather than affecting the present one. Artificial gravity. Speculative technologies for navigating cosmic frontiers. Despite its importance, gravity remains one of the least understood forces in physics. Unlike electromagnetism, which can be controlled and manipulated through technology, gravity is something humans have never been able to create or modify at will. The dream of artificial gravity has long been a staple of science fiction, from rotating space stations to mysterious gravity generators. But could technology one day make it a reality? In space, the absence of gravity creates significant challenges for both astronauts and spacecraft. The human body is adapted to Earth's gravitational pull, and extended time in microgravity leads to serious health effects. Muscles weaken, bones lose density, and fluids shift in unnatural ways. Long-term exposure to weightlessness could have lasting consequences, making artificial gravity a key factor in any future plans for deep space travel or colonization. One of the most practical and well-studied methods for simulating gravity in space is centrifugal force. If a spacecraft or space station spins at the right speed, the outward force generated by the rotation can mimic the effects of gravity. This concept has been explored in films like 2001, A Space Odyssey, where a giant rotating station provides an Earth-like environment for its inhabitants. Scientists have studied similar designs for future missions, with proposals for rotating habitats that could create artificial gravity through spin. The physics behind this idea is straightforward. When an object moves in a circle, it experiences an outward force. In a spinning space station, this force pushes everything outward, pressing objects and people against the floor of the station's outer walls. The faster the rotation, the stronger the effect. However, spinning structures come with engineering challenges. The rotation rate needs to be carefully controlled to avoid motion sickness, and the station must be built large enough to provide a smooth, natural effect. Small rotating habitats might create uncomfortable forces, making people feel dizzy or disoriented. Since gravity and acceleration are closely related, it might be possible to simulate gravity by using electromagnetic fields to push or pull objects in a controlled way. Some futuristic concepts suggest using superconducting magnets to create forces that could simulate weight for astronauts. These ideas are still speculative, but they open up the possibility of creating artificial gravity without relying on large, rotating structures. The most ambitious approach involves manipulating gravity itself. Current physics suggests that gravity is caused by the bending of space-time. Some theories propose that if space could be manipulated in the right way, perhaps using exotic materials or high-energy fields, it might be possible to create artificial gravity fields. If scientists can one day understand how to generate and manipulate gravitational waves, it might be possible to create artificial gravity by producing controlled distortions in space-time. In certain quantum gravity models, gravity may emerge from deeper physical principles that are not yet fully understood. If a connection between quantum mechanics and gravity can be established, it could lead to entirely new technologies capable of generating artificial gravitational fields. For now, the most realistic approach to artificial gravity remains centrifugal force. NASA and other space agencies continue to explore ways to incorporate rotating habitats into future space missions. Concepts for Mars-bound spacecraft, for example, have included designs where sections of the ship rotate to provide artificial gravity for the crew. Even if full artificial gravity technology remains out of reach, using rotation-based systems could significantly reduce the health risks of long-term space travel. The simulation hypothesis. Are we living in a cosmic construct? Philosophers have long questioned whether the world we perceive is truly real or just an illusion created by our minds. In recent years, this age-old debate has taken on a new technological twist. The simulation hypothesis suggests that our universe, everything we see, experience, and even ourselves, might be part of an advanced computer simulation created by a far more developed civilization. One of the main arguments supporting this idea comes from the rapid advancement of technology. Over just a few decades, humanity has gone from simple 8-bit video games to hyper-realistic ray-traced virtual worlds. If this trend continues, it seems possible that future civilizations, whether human or alien, could create simulations so detailed that the inhabitants within them wouldn't even realize they were inside a simulation. If such technology is possible, then the question arises, could we already be inside one? Mathematician and philosopher Nick Bostrom proposed a famous argument suggesting that at least one of the following must be true. Either civilizations never reach a level of technology capable of running detailed simulations, they choose not to run them, or we are almost certainly living in one. If highly advanced civilizations exist and create countless simulations of past worlds, then the number of simulated beings would vastly outnumber those living in a real base reality. By pure probability, we would more likely be one of the simulated beings rather than one of the rare, non-simulated ones. There are strange patterns in physics that some believe hint at a programmed universe. The fundamental constants of nature, such as the speed of light and the strength of gravity, appear to be finely tuned for life to exist. If any of them were even slightly different, stars might not form, atoms might not hold together, and life as we know it would be impossible. Some scientists argue that this fine-tuning suggests a deliberate design, possibly the work of a simulator setting the rules of our world. Another possible clue comes from quantum mechanics. At this scale, particles do not seem to exist in definite states until they are observed. Before measurement, they exist in a range of possible states, almost as if reality does not render them until someone looks. This is similar to how video games save processing power by only generating parts of a game world when the player is nearby. Some researchers have speculated that this effect could indicate that our reality operates in a similar way, conserving resources by only loading details when necessary. Further support for the hypothesis comes from the concept of digital physics, the idea that the universe itself might be made up of discrete pixel-like units of information, rather than being a continuous, smooth reality. Some theories suggest that space, time, and energy could be fundamentally made of tiny bits of data, just like the pixels on a screen. If this is true, then our universe could be running on a form of computation far beyond our understanding. Experiments have been proposed to test whether we live in a simulation. One idea is that if our reality is simulated, there might be detectable limits to how much detail the simulation can handle. Scientists have suggested looking for unusual patterns in cosmic rays. If these particles behave in ways that suggest an artificial structure to space itself, it could be evidence that we are inside a programmed environment. But there are strong arguments against the simulation hypothesis as well. Some physicists argue that the universe's complexity is far beyond anything that could be simulated, even by a super-advanced civilization. the amount of data required to track every particle, every star, and every moment in time would be staggering. Even if future civilizations could build vast computational systems, running an entire universe within a universe might be too much to handle. There is also the question of motive. If we are in a simulation, who or what created it and why? Some suggest it could be an experiment with advanced beings studying the development of civilizations. Others believe it could be a form of entertainment, much like we create video games for fun. Some think that the simulation could be a test, designed to observe how beings behave in certain conditions. But without evidence of a simulator's presence, these ideas remain mere speculations. If we are living in a simulation, does it change what it means to be real? Would it mean that our actions and experiences are less meaningful, or would they still matter just as much? And if we ever discover proof that we are inside a simulation, what would happen next? Would we try to communicate with the creators, break free from the system, or simply continue living as we always have? Exotic states of matter, beyond the known frontier. Matter comes in familiar forms: solids, liquids, gases, and plasmas. These are the states we encounter in daily life, from the water we drink to the air we breathe. But under extreme conditions, far beyond what we experience on Earth, matter behaves in ways that challenge the limits of physics. Scientists suspect that entirely new and exotic states of matter might exist, forming under intense pressures, temperatures, or energy levels. Some of these states have been theorized, while others may remain undiscovered, waiting for the right conditions to be observed. One of the most intriguing examples is Bose-Einstein condensates. First predicted in the early 20th century and created in laboratories decades later, these are strange collections of atoms cooled to nearly absolute zero. At such low temperatures, the atoms stop behaving as individual particles and merge into a single quantum state, essentially acting as one unified entity. This leads to bizarre effects, such as atoms moving in perfect unison as if they were one massive particle instead of many separate ones. Bose-Einstein condensates provide a glimpse into quantum behavior on a macroscopic scale, making them a bridge between everyday physics and the deeply strange world of the quantum realm. Meanwhile, quark-gluon plasma represents the opposite extreme, an unimaginably hot and energetic environment. Scientists believe that moments after the Big Bang, the universe was filled with this plasma, where protons and neutrons had not yet formed, and instead, the fundamental building blocks of matter, quarks and gluons, existed freely. By smashing particles together in powerful accelerators like the LHC, researchers have recreated tiny flashes of quark-gluon plasma, lasting for only fractions of a second. This allows them to study how the early universe evolved, and how matter came to take the forms we see today. At the core of neutron stars, pressures are so immense that normal atomic structures collapse. Some theories suggest that within these stellar remnants, strange matter could exist, a form of matter where subatomic particles are squeezed into an ultra-dense stable state. If strange matter exists, it could have properties unlike anything known, possibly forming the densest material in the universe. Another possibility is the existence of supersolid matter, a state that combines the rigid structure of a solid with the frictionless movement of a superfluid. Superfluidity itself is already a strange phenomenon, where liquids like helium, when cooled to extremely low temperatures, flow without resistance, defying normal behavior. Supersolids, if confirmed, would represent an even stranger state where atoms are locked in a rigid pattern but still flow effortlessly through one another, as if obeying two contradictory laws of physics at the same time. Scientists are also exploring the concept of time crystals. Unlike ordinary crystals where atoms are arranged in a repeating pattern in space, time crystals form a repeating pattern in time. This means they oscillate between states without any external energy input, defying normal expectations about thermodynamics. Although early experiments have suggested that time crystals can exist under very specific conditions, their full implications are not yet understood. Beyond laboratory experiments and stellar environments, there could be even more extreme states of matter lurking in the cosmos. Theoretical physicists have speculated about Planck stars, hypothetical objects that form when a black hole's core compresses to an unimaginable density, leading to a state where quantum gravity effects take over. If such objects exist, they could provide a missing link between quantum mechanics and general relativity. There is also the possible existence of negative mass matter, a type of matter that would behave in an opposite way to normal matter. Instead of responding to gravity by being pulled toward other objects, negative mass matter would be repelled, leading to strange effects that challenge our understanding of inertia and motion. Some of these exotic states will have practical applications. Superconductors, materials that allow electricity to flow without resistance, are already used in advanced technologies like MRI machines and particle accelerators. If scientists can develop room temperature superconductors, it could revolutionize energy transmission, making electrical systems far more efficient. Likewise, if we learn how to harness quark-gluon plasma or manipulate strange matter, entirely new fields of physics and engineering could emerge. But on that note, today's voyage comes to a close. Were there any unresolved mysteries that we missed? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.